Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI-generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In the previous video, we used the math kernel library, MKL, to perform matrix multiplication with OpenMP for parallel computing. Now, we will conduct a scaling analysis of OpenMP with MKL on Olivia. This involves measuring computation times with varying numbers of threads, starting from a single thread and scaling up to 256 threads. Scaling analysis in parallel computing is a method used to evaluate and understand how efficiently a parallel system performs as the number of processing units increases. It helps determine whether adding more computational resources improves performance and by how much. Scaling analysis is crucial for optimizing parallel systems and ensuring that resources are used effectively. I am already logged in to Olivia and currently inside the MXM OpenMP folder. Let me list the folder contents. I will approach the scaling analysis differently from what was done in videos 12 through 16. This involves using a script named Testing OpenMP. Let's take a look at this script. The script is very similar to the MKL job script I used in video 43. The first difference is that it requests one node, but the number of tasks and CPUs per task, or threads, is specified differently and not directly in the script. The second difference is that the job requests 753 gigabytes of memory. In previous videos, I used job scripts that requested 100 gigabytes, which was sufficient since the job used about 44 gigabytes in video 43. According to the web documentation pages, the normal CPU compute nodes have 768 gigabytes of available memory. However, some of this memory is reserved for the Linux system, leaving approximately 753 gigabytes available for jobs. In the scaling test, I will submit jobs using a varying number of cores, ranging from a single core to 256 cores. As a result, some jobs will not utilize all the cores on a node. This could potentially result in other jobs being assigned to the same node as our jobs, or even multiple jobs from our scaling test being assigned to the same compute node. To avoid this, I request all the available memory during the scaling test. By doing this, I ensure that no other jobs are allocated to the same node, preventing any potential impact on data transfer between memory and cores, which could affect the performance of our test. This ensures that each scaling test job is executed exclusively on a single compute node. The third difference is that the script does not compile the Fortran program. Instead, it uses the executable MXM generated in video 43. However, even though the job script is not compiling the Fortran program, the executable still requires the modules. This shows that the modules are not only necessary for compilation, but are also needed to execute the compiled Fortran program. The program is executed 3 times, and these wall times can be used to calculate an average for the matrix multiplication using MKL with OpenMP. The job scripts conclude by echoing some Slurm variables to the job output file. After reviewing the testing OpenMP script, I exit the Emacs editor and return to the terminal. I will also use a Python script named setup testing OpenMP for the scaling analysis, so let's take a look at it. The script uses the OS module to execute Linux commands. It defines an array called threads, which contains the 9 different number of threads to be used in the scaling analysis. The task variable is set to 1, as I am using a single task for multi-threading on a single node. The script then defines text variables to specify the number of tasks and CPUs per task, or threads. The script also defines a text variable to store the name of the job script I just reviewed. A Python for loop is used to execute the sbatch command 9 times, corresponding to the 9 different values in the threads array. Each sbatch command is printed to the terminal before being executed using the OS module. I will now exit the Emacs editor and return to the terminal, where I will clear the terminal. I will start the scaling analysis by executing the Python script. However, the execution fails, and the terminal displays the message, "No such file or directory." This happens because a Python module is missing from my environment. To confirm this, I list the currently loaded modules using module list and see that no Python module is loaded. I then load a Python module with module load. I verify its presence by using module list again. As shown, Python version 3.11.7 is now loaded. Let me save these modules as my new default home environment, as I will need the Python module in the upcoming videos. I will attempt to execute the Python script once more, but first I will clear the terminal. I execute the Python script once more. This time, the terminal displays the sbatch commands executed by the script. We can see that the number of tasks and CPUs per task is now specified on the command line when submitting the testing script. Using the sq command, I can confirm that all my jobs have started. Note that all 9 jobs are assigned to different nodes. I ensured this by having each job request all the memory available on a single CPU compute node. Before checking the results, I will clear the terminal. I will first list the folder contents with the ls command. Let's examine the last job output file using the more command. From this file, we can see that using 256 threads with MKL results in a wall time of approximately 5 seconds. Once again, we observe that the memory usage has increased to approximately 44 gigabytes when using MKL. This increase in memory usage is a trade-off for improved performance. The MKL library utilizes additional memory for temporary buffers, data alignment, parallelism, and other optimizations that greatly enhance the speed of matrix multiplication. I used the data from these scaling tests to create figures showing the wall time and CPU time, similar to what was done in videos 12 through 16. The first figure displays the wall time and CPU time, with a logarithmic scale on the time axis. The second figure presents the same data but uses a logarithmic scale on both axes. Let me first enter the number of threads or cores used in the scaling analysis. I can add the mean wall times to the figure. I will also enter the CPU times, which are calculated by multiplying the wall times by the number of cores used. Finally, I include the speedup factors between tests. The reason for plotting the CPU time is that this curve would form a straight line if the scaling analysis had shown a perfect speedup factor of 2 for all tests. We observe a near-perfect speedup up to 16 cores. The scaling analysis shows that a computation taking about 597 seconds on a single core is reduced to approximately 39.7 seconds on 16 cores, achieving a speedup of around 15. In an ideal scenario with perfect speedup, this would have been 16. The speedup decreases when scaling from 16 to 64 cores. The scaling analysis indicates that a computation taking approximately 39.7 seconds on 16 cores is reduced to about 12.4 seconds on 64 cores, achieving a speedup of roughly 3.2 instead of the ideal speedup of 4. The speedup diminishes further when scaling to 256 cores. The scaling analysis indicates that a computation taking 12.4 seconds on 64 cores is reduced to approximately 5.04 seconds on 256 cores, achieving a speedup of 2.5 instead of the ideal speedup of 4. The scaling analysis reveals that a computation requiring 597 seconds on a single core is reduced to 5.04 seconds on 256 cores, resulting in a speedup of about 119, which is below the perfect speedup of 256. A perfect speedup is unattainable because, as explained in video 11, there will always be sections of a program that cannot execute in parallel. These sequential sections increasingly limit the speedup factor as the number of cores used for parallel computing grows. As observed in these scaling analyses, there is near-perfect speedup up to 16 cores, but this diminishes when scaling to 32 and 64 cores. The speedup factor declines even further when utilizing 128 and 256 cores. In the next video, we will explore the performance of the Intel compiler when using the triple nested loop for matrix multiplication. The Intel Fortran compiler will be loaded through the NRIZ module system. I am looking forward to the next video. Wishing you all happy computing in the meantime.